All right, it's 2 o'clock, so let's get started. So quiz 5's out tomorrow, just as always. It's due on Saturday as usual. Homework 2 part 2 is due on Sunday. So how many of you actually did something of part 1? Okay, so about the majority. So for those of you who didn't, I would highly recommend you do. We get really good feedback from graders, but it's really worth the time to do that. Any questions about anything homework 2 part 1? Anything? Yeah.
So for number 2, like 2 and 3, so the NFA that he gave us, there's the Q4, it doesn't lead, just no out transitions from it. When we're ripping out states, what do we do with that? Do we just like rip it out and like leave it alone?
With Q4, since there's no way out of it, how many transitions am I going to add again? 0.
Okay.
So it effectively does not matter. Any other questions? And since it's a non-final state, there's no way to get to the final state anyway, so it would have to be done. Any other questions? Okay, so what was the major thing we talked about in class last week?
Something?
Yeah, something with lemmas. What kind of lemma?
Pumping.
A pumping lemma. Ah. Because I know so many lemmas so far. Actually, I know a whole bunch, but in this class, we only have one so far. So what does this really tell us? What did it tell us? Yeah, so it said it helped us prove something to be not regular, right? There's no DFA for it. But what does it actually say?
If it is regular, there's pumping length.
Right, so if I do have a regular language, then I actually can understand some properties of that language. So if L is regular, then as was the suggestion, there exists a pumping so-called constant, which we're going to call P for L. Okay? And what did that pumping constant P remind us of? What is it really an indicator of? Yeah, so since L is regular, there must be some DFA for it. And then therefore, it has some number of states. I'm imagining P to be the number of states in the DFA. And so why do I want P to be the number of states in the DFA? Then what type of behavior are we trying to see when we feed strings into this DFA? Yeah, we want this state to be repeated, right? Because what we want this lemma to say is, if I know what happens if I feed really long strings into this DFA, then I know what a lot of other strings are going to look like. And so our picture that we had was, we had this start state, middle state that is going to repeat, and there must be some way to get from the start state to this repeating state. Let's call it X. I said it repeated, so it comes out and comes back to that same state. I'm going to call that part Y, the string that you read from that state back to that state. And then I want to say something about strings in the language, right? So I need to be able to accept this string that I'm considering. And I'm going to call this part Z. Okay? So I can say right now that X, Y, Z is in the language, because if I just read off each of the paths in order, I end up in a final state. Well, what does that tell me? How did I even get to this point of this repeating state? How can I guarantee that there's a repetition? What's that? Yeah, pigeonhole principle, but what about the string that I fed into this thing? What characteristics does it have?
It's part of the language.
What was in the language? Well, so that's one thing. So
It's like least P length.
yeah, so for all W in L, and what was the other thing you said?
Least length P.
Yeah, I want to be at least the number of states in this DFA because I want a state to repeat. Because if I have a state that I can repeat, then I can just go around this loop as many times as I want and get more strings in the language. I want to be able to understand the structure of the strings in the language. So I need to consider the strings that are in the language, so I end up in an accept state, and that are long enough, which means that they will repeat a state in the corresponding DFA. Okay? But I'm not going to be talking about a DFA, I'm just talking about this concept. Okay, so for every single string in the language that repeats a state, it looks like it's going to do this repetition. Well, how do I find this X, Y, Z part in W? Well, I know that W, and this, such that, well, I know that W is equal to X, Y, Z because I just considered a string in the language that's long enough. Well, that's just X, Y, Z. But how many decompositions of X, Y, Z are there? Many, right? Do I need to consider just one or every possible way? Ooh, be careful. Is it just one or many? It's just one, right? Because if I could find some way to decompose it like this, then I can find this Y part. And then we'll see when that contradiction comes the other way in a second. But such that there is a way. I didn't say that there are many ways. I just said there's at least one way to write W as X, Y, Z. So in those three parts, such that, and then we have the three conditions. Well, let's see. How can we derive these three constraints, I guess? Well, what can I say about the string X, Y, Y, Z? Is that in the language? Yeah, because it effectively just means going around that loop twice. What about 3 Y's in the middle? Yeah, what about 0 Y's? Yeah, I don't have to go around this loop, provided I have the right string, but XZ is in the language too. Okay, well that tells me that for any number of Y's that I pick, it will always stay in the language. If I find this XYZ, no matter how many Y's I put in, it'll always stay in the language. So it's in L for all I at least 0. Okay? Because I can go around that loop as many times as I like. Well, how did we find the other 2 conditions? Well, let's see. In the original string, was Y the first repetition? Maybe. Might be the last one, might be the middle one, might be the first one. Well, let's consider if it was the first one. I said that this works for all strings of length at least p, right? Does it work with strings of length exactly p? Yeah, I said at least p, so exactly p works. But if it has length at exactly p, does it have a repetition? Yes, because if I have a string of length exactly the number of states, how many states will I see in the computation? The number of states plus 1. So that must mean I see a state twice. So if I have a string of length exactly p, then that Y part better be within the first p characters, right? Because that's the repetition part. Oh, but that means X came before Y. So what can I tell about the length of X, Y together? It has to be at most p, because if I work with strings of length exactly p, there must be a repetition within the first p characters. Okay? So therefore we can say that X, Y's length is at most p. So the repetition part, there may be many repetitions later, but I can guarantee a repetition within the first p characters. Okay? What about the second condition? Y can't be empty. So another way to say that is Y's length is at least 1, or Y is not empty. And so why would we want that to be true? Suppose if it were empty, well, what does this third one tell me then? Insert as many copies of empty string as you like. What's that going to do? Nothing, right? So it's not really telling me anything about other strings in the language. It only tells me about one particular string. So that's why we require it to be non-empty. Okay? Does that make sense? Any questions about that? Any of this? That's right. This is the hardest topic for students, so please ask questions if you have any questions. Okay. So let's do some of the problems. So the first one is, we did 0 to the n, 1 to the n in class. I'm going to extend it by saying 0 to the n, 1 to the n, 2 to the n. Equal numbers of zeros, ones, and twos. Zeros are followed by ones, which are followed by twos. So I want to prove that this is not regular. And then I can just say, oh, yeah, that's the proof. It's not regular. I claim it, and therefore you must believe me, right? How would I prove this? Well, let's see. The claim is it's not regular. And I look over here and I say pumping lemma. It says L regular implies other things. Oh, I can't use the pumping lemma directly, right? Because I don't even know if it is regular. I can't apply it.
Suppose to the contrary.
Oh, okay. Let's suppose to the contrary that it were regular. And if we get a contradiction, what can I conclude?
It's not
It's not
regular.
regular. So let's suppose L1 were regular. Well, what can I immediately figure out from that first statement?
There exists a string W at least length P.
Well, what's P?
There exists a P.
Yeah, there exists a pumping constant P. That's what I wanted. So exists a pumping constant P for L1. So all the proofs we're going to do today follow the same guideline. Suppose it were regular, then there's a constant P per hour. The language name. Okay, well, let's see. It says that, pumping lemma says that for every string in the language that's long enough, effectively I can pump that string. There is a way to pump that string. Well, I'm trying to get a contradiction, right? So it says it works for every single string in the language, every one that's long enough. But if I show you one that's in the language and long enough that doesn't pump, is that a contradiction? Yeah, because it just said every one works. I found one that doesn't. So let's find a single string that won't work. But remember, I gotta pick it so that it's in the language and long enough. So any example strings that would work for this. So I know on the midterm I'm gonna see this. So I'm gonna choose W. Let's pick this string. It's in the language. Is it long enough? No, why?
It's not length P.
Yeah, P might be 10 trillion for all I know, right? I don't know that here. But can I modify this so that I can guarantee it has length at least P? 0 to P, 1 to P, 2. It's still in the language, but now it definitely has length at least P, which is exactly what I want here. Okay, so let's see. Hopefully I can get a contradiction out of this. And so it says there is a way to write W as X, Y, Z such that you can pump it. It says that there is a way. But if I can show you for this string right here that there's no single way to pump it, there's no way to pump it at all, I think that's a contradiction, right? So I gotta look at every way to decompose the string into X, Y, Z. Every single one. I can't leave any of them out because if I leave one out, it might be the one way that works. Okay? So what do you think are the decompositions? this one will help. So let's see. Is x, y the prefix of the string, or a prefix of the string? Yeah, it's the beginning of the string. Oh wait, it says that its length is at most p. What does that tell me about x and y? They're all zeros, right? I set this up so that all the first p characters are zeros. That forces x and y to be all of the zeros, okay? Well, let's see. I know it's entirely consisting of zeros, x and y, but I need to handle every single way, every way to decompose it. So let's just say that it's some integer a for a at least 0. We're not going to use the fact that a is at least 0 here, but it's just important to know that. But we also know that y is entirely of zeros also. It may be the same number of zeros as x or a different number. But let's just say that it has b zeros, for instance. What do I know about b? Great. That was like harmonious. Right, so b is at least 1. Okay, well, what does that tell me about z then? Well, there are only 3 parts of the string. I think z is the rest of the string, right? Well, let's see. I know it's going to contain all the 1s and 2s, but it may have some zeros also. Well, let's see. I started with p zeros. I took away a for the x part. I took away b for the y part. So I think I still have p minus a minus b zeros left over with all the 1s and 2s also. Okay? Okay, so I'm handling every possible decomposition here according to the rules that we set out. But now let's think about this. Where is the contradiction going to come from here? Yeah, the third condition is going to get us, because we used the first 2 to find the string and the decomposition. I think the third one's going to help us here to get a contradiction. Well, let's see what it says. It says, no matter how many copies of y that I put into the string, I stay in the language every single time. But if I can find you a value of I for which I get out of the language, this all is not true anymore, and therefore I have a contradiction. So, what value of I do I have right here? 1, right? I only have 1 copy of y, so I better not pick 1. Any other suggestion? 2. It'll actually turn out that every value other than 1 works, so it'll be hard to find out one that doesn't. But let's just choose I equal to 2. I could have picked I equals 0, 3, 4, any of them will work. Well, let's see what happens. Let's see what happens. X, y squared, z. Well, what does that mean? That means just I have a copy of x, which is just a zeros in a row. I have 2 copies of y. Well, y is just b zeros in a row. So I have 0 to the b, 0 to the b, twice. And then I have z trailing off at the end. And that was just p minus a minus b zeros, p1s, p2s. Okay? Well, let's simplify. Squash all the zeros together. Well, I think this set of a zeros cancels out with this minus a over here. So I'm going to cancel those out. And I think this minus b cancels out with one of the b's here. So I think those go away too. So how many zeros do I have left? P plus b, zeros left. And then since I never touched the 1s or 2s, I still have p of those. And so now is our check. I want to see if this string is not in the language anymore, or if it is. What's the only way that this could be in the language?
E0.
Well, let's back up one step. Well, I think it better be true that this quantity is equal to that quantity or the other one, because they have to all be the same. So this implies that p plus b is equal to p, but then, as we all figured out, subtract p from both sides, I have b is 0. But obviously, that can't happen because b was at least 1. So that's the only way it could have stayed in the language. So what can I conclude about this string? It's not in the language, right? So this is not in, I called it L1. So what can I conclude about L1 then? It's not regular. Okay. L1 is not regular. Okay. Everyone understand how we got that? Yeah.
So why is x, y 0?
Oh, can you repeat that, sorry?
Why is x, y 0? Like, how did you get x, y to 0? How did you set that?
Well, since the first p characters are zeros, and I know that the prefix x, y has length at most p, they must all live within the first p characters, which are all zeros. So that's why they're all zeros, but then again, I gotta handle every possible way to break that. So that's why I said arbitrary numbers. Any other questions? Okay, so let's do this slight modification, very close. I have 3 n zeros, 2 n ones, and n twos. So just more ones than zeros than we got. So how do I start this off again? Suppose it's, well, I want to say that this is not regular, but how do I start through is what I meant. Suppose it were, and what can I conclude from that? There's a pumping constant for, it's a different language this time, but L1 prime. There's no point in rewriting a proof that has the same parts, but. Okay, well, I picked a W before. Can I use the same W here? I picked 0 to P1 to P2 to P before. Can I use it over there? No, why? It's not in the language. So what's the better choice of a string then? Any guess? Here's a tip. Anytime you see n in the exponent, put p there. Okay?
Does that work every time?
Not always, but I'd say 98% of the time it works that way. The trouble is if you have, if the language is actually finite, then therefore it's regular, or if you have two things working together. But most of the time it works. So what would be a good string for this? 0 to 3p, yeah, you know, 1 to the 2p, 2 to the p. And that's certainly in the language and definitely has length at least p, so we're fine there. So, is anything gonna change about my decomposition? What's gonna change?
Z.
Oh, I think the number of zeros in Z and the number of ones in Z is gonna change. But X and Y are gonna stay the same. So X is still gonna be some number of zeros. Y is still gonna be some other number of zeros possibly. And Z, but now is gonna be 3p minus A minus B, 1 to the 2p to the p. Almost exactly the same. So now I gotta find a value of I that works. It turns out any one other than 1 will work, so any guess? Any choice? Any choice?
7.
7, perfect. Last recitation picked 4, now it's 7, now it's gonna go up by 3 every single one, I guess. But let's just choose I equals 7 now. Well, let's see, that's X, Y to the 7th, Z is, well, I have X copied down here. 7 copies of Y, I'm just gonna shorthand that with 7b up in the exponent instead of 7 literal copies. And then Z, which is right here. So I have 0, 3p minus A minus B, 1 to the 2p, 2 to the 3. Almost exactly the same, other than the value of I. Well, again, I think the A's are gonna go away. And I think one of the B's is gonna go away here. So I think when the dust settles, I have 3p plus 6b very hard to say, zeros left. And hard to write too, apparently. I haven't touched the ones, and I haven't touched the twos either. Okay? Well, what's the only way that this could stay in the language? Well, let's see. The only way that this could be in the language is if 3 times the number of 2's is equal to the number of zeros, right? That's the only way. Well, there are other things, but that's certainly a condition. Well, this implies that 3 times this number better be equal to this number. So 3p plus 6b better be 3 times that guy, which is 3p. And then what can I conclude from that for b? It better be 0, but obviously that can't happen. So that's the contradiction. So what can I conclude about L1 prime? It's not regular either. Good. L1 prime is not regular. Okay. Everyone good with that? Okay. So now let's do the 2 more interesting ones, and I find these really, really cool because it's not exactly the same as this, but it requires you to think a little bit about how to do it. But hopefully it won't be too bad. So this one says that I am only considering strings of pure zeros, right? There's no 1's or 2's here. And the number of zeros is a perfect square. So 0 zeros, which is the empty string, that's in there. A single zero's in there, 4 zeros are in there, 9 zeros in there, etc. Okay? And I claim that this is not right there. Okay? So how should I start this? Suppose it were. So I'm going to actually write it out this time because it bears seeing. So suppose L2 were regular, and then same thing as before, there exists a pumping constant P for call it L2. What's my next step? I better pick a string that what has what 2 properties? In the language and
Perfect.
long enough length at least p. So let's choose such a string. And inevitably on the midterm or even the final, someone's going to put this. They say, oh, it has length at least p. That's a good string. What's wrong with that string? It may be a perfect square. It might not be. I don't know. I can't guarantee that it's in the language. Is there a way I can modify that so I can guarantee for sure it is? P squared, right? If I force it to be p squared, then p is an integer, so p squared must be a perfect square, and I have to be zeros. So therefore, this must be in the language. Okay? Well, let's think about the decompositions again. Do I know anything about what x and y are going to be? Zeros. Are they going to be anything else? No. Sometimes working with what are called unary languages are a lot easier because there's only one character. So it makes this decomposition a lot easier. So let's say we have a zeros again, y is b zeros, and then z is going to change a little bit because I started with p squared. I took away a, I took away b, so I have p squared minus a minus b. Okay? So, last 2 examples, I let you guys choose the value of I. Now it's my turn to give you a value of I. So, actually any one other than 1 will work. It's just the details are a lot harder to work with than the one I'm going to use. So I'm going to choose I equals 2. Okay. Well, let's look at this string. It's x, y squared z, as usual. So let's just put everything together. So it's 0 to the A, 2 copies of y, so 2b zeros, then the p squared minus a minus b left. Then if we simplify, we're going to end up with c squared plus b zeros. Because one of the b's goes away and the a's go away. Okay? What's the only way that that string could be in the language? What's that? But b could be positive. It might be a perfect square. Right? It might be equal to the next perfect square, maybe. I don't know. Well, let's see. Let's see what happens. But everyone just said that it can't be equal. Let's just compare the two values, p squared and p squared plus b. Can they be equal? No. What would that imply if they were? It would be a 0. So I think I can say that this is a strict inequality. Right? Because I'm adding something positive, and I'm always adding something positive. But it definitely is not equal to that perfect square. But you say it might be equal to some other perfect square, right? Well, let's see. What is the next perfect square after p squared? P plus 1 squared. Well, let's figure out what that is. Well, that's just p, oh, I should do it this way. P plus 1 squared. Then let's put on our middle school algebra hats on, and then boil this out. So what does this become? Right, p squared plus 2p plus 1. Let's see. That p squared plus b may be equal to this. I don't know. Let's see. What's the largest value that p squared plus b could take on?
P squared plus B.
Right, it's p squared plus b. P itself is fixed. That'll never change, but b can. And we know over here, can x be empty?
Yeah.
Yeah, I never said x had to be non-empty. I said y had to be. Can y have length exactly p? Yeah. So that tells me that this can be less than or equal to p squared plus p. Right? Oh wait, I see a p here and a 2p here. I know that, therefore, this is definitely an inequality with p squared plus 2p plus 1. Is it a strict, or do I have to put an equals on there? It's a strict inequality, and why is that? It's the plus 1 at the end. Definitely, if p were not 0, then the 2p is going to win, right? Because it's going to add something more. But if it were 0, then this is 0, and then this is 1. So it's a strict inequality. Okay, let's see. What was the length of the string that we just found? It was this path, right? Can it be equal to a perfect square? Well, let's recap. It's not equal to this one, and it's definitely not equal to this one. Are there any in between? No, because what did I ask? I asked for the next perfect square. So it's strictly between two perfect squares and not equal to either of them. So I can conclude that p squared plus b is not a perfect square. What can I conclude from that? It's not in the language, so definitely x, y squared z is not in, I called it L2, and therefore I can say L2 is not right. Okay, so it's not exactly the same, but what we were looking at is the string that we got. What's the only way it could be possibly in the language? And then we noted that the only way it could be is if it was a perfect square, so we can compare two consecutive perfect squares showed it wasn't equal to either of them and between each. Okay? Any questions about that? This one is in the book, so if you're confused by it, I highly recommend reading that. No other questions? All right, let's do one that's even cooler, in my opinion. So you certainly get the flavor that these regular languages, these DFAs, are really, really simple and not very powerful. Because we can't even recognize whether something's a perfect square or not, which is kind of sad in my opinion. And what's even worse is this one, which is 0 to n, where n is a prime number. Okay. How does this one start again? Yeah, just do this regular. So assume LV were regular, no problem. And from that, I can say exists a pumping constant P for L3. What's my next step? Choose a string. So let's choose a string. And then I definitely know if this was on the test, someone will say that string. P stands for prime, and so therefore this string is in the language. Is that a problem? Yeah, I don't know if P is a prime number. It's definitely long enough, but I don't know if P is a prime number. So how can I fix that? Someone said P plus 1, would that work? Can I guarantee a prime's at least P? Does anyone know the infinite primes proof by Euclid? Someone said no. But it essentially says that no matter what integer you find, there's always a prime number larger than it. Maybe I could just choose that prime number. Okay? Well, I can't choose P necessarily, but let's just choose the prime right after it. I know there is one, so let's just choose it. So let B, no, I'm going to call it R, sorry. Let R be any prime at least P. I'm going to make one small, tiny modification to this, and we'll see why in a second. I'm going to make it at least P plus 1. Can I still find a prime at least P plus 1? Yeah, there are infinitely many primes. All of them can't live below P plus 1 because P is a finite integer. So there is a prime, such a prime R. So I'm perfectly fine in saying this. It's also long enough because it's at least P plus 1 in length, so I'm perfectly okay there. Well, let's see. What do I want from this? What I want is to look at every single decomposition. Well, I'm not going to look at the specific decomposition because I only will care about the length of the string. I'm not caring what the string is. I'm just caring about its length. Okay? Well, let's see. Actually, no. I should make this at least 2. We'll see why in a second. Sorry. Well, let's see. What is the length at most of xy? P. It's not a trick question, right? It is the length at most P. Can I infer anything about the length of z here? Or a lower bound on it? Yeah, well, what's the smallest value that the length of z could be? 2, right? That's the smallest. It might be larger, but that's the smallest it can be. So we can see from this that the length of z is at least 2. Okay. What does that tell me about the length of xz? It's also at least 2, right? Because because x possibly could be empty. I don't know that. I am treating every single case here. X could be any range of values, y could be any range of values, and z is the rest of the string. I know this is true for every decomposition. Okay, well, I don't know yet the value of I, so let's just look at it in general. So I want to look at x, y to the I, z. But again, I'm only concerned about the length of the string, not the string itself. I could be concerned with the string since it's only zeros, but I'm making my life easier. So let's look at the length of the string. Would you agree with me that this is equal to the length of xz plus the length of y to the I? Would you agree with me with that? I'm just adding up the length of the xz part plus the length of the middle part. Yeah, that's certainly true. Would you agree with me that this is equal to xz's length plus I times the length of y? I think so, because y to the I, that's just y concatenated with itself I times. Well, that's just the length of y times I, because I'm just concatenating them all together. Okay, well, let's see. What do I want from this? I want to find a value of I such that this value is not prime. Okay? Any suggestion? Here's a suggestion. What about I being equal to the length of xz? Can I choose that one? I think so. Is x's length a finite integer? Yeah. Is z's length a finite integer? Yeah. Is the length of them two together? Yeah. It's a finite integer. Could I choose that one? Yeah, there's nothing that says that I had to pick a very specific number for I. I just found an I right here. Well, let's see what happens. Well, just substituting that in, that's just xz's length plus xz's length again times the length of y. Can I simplify this a little bit? Yeah, how can I simplify it? I can factor out the xz part, right? Because it is common in both of the parts. So if I factor out the length of xz, what do I get for the first term if I factor out an xz? It's like 1. Plus, what would the second one be? Length of y. Okay. Okay. What is this? What is the length of xz?
Greater than or equal
Greater
to
than or equal to 2. That's all I know. What is this? Do I know the length of y? Or a lower bound on it? 1. What's the smallest value that 1 plus the length of y can take on? 2. So I've just made a string that is the multiplication of something at least 2 and something else also at least 2. Can that number be prime? Something that's greater than 2, greater than or equal to 2, times something else also greater than or equal to 2.
No.
Can that number be prime?
No.
No, why? Because a prime number is defined to be something that's divisible by 1 in itself. Note that if I left this to be 1 right here, that these guys would be 1, then I can only conclude that this is at least 1. And then you can say, well, this could be prime because this could be length 1, and this could be whatever, the actual prime's length. But by putting this to be at least p plus 2, this has to be at least 2, and therefore this multiplication results in a number that's not prime. Okay? So therefore, I can conclude that this number is not prime, and also I can conclude that L3 is not regular. Okay? So it's not every single time that you have to pick a value like 7 or 2. You don't have to pick a fixed value every single time. What you have to pick is some finite integer. And I picked a finite integer, and the way I wanted it was I wanted to factor it with the existing thing that I had, such that both parts have length at least 2. And since it's the multiplication of two things that are at least 2, it can't be a prime number, which is the conclusion I wanted. Any questions about this? I know this one's a little bit more convoluted than the others, but any questions? All right, I think we have time for the last one. So this one will go really quickly. So let's see. So this one is number 5. L4 is W in 0, 1 star. W has same number of zeros and ones. It's not good. All right. I could go through a pumping lemma style argument again, but I don't want to here. So how do you think I can go about proving that this is not regular a different way? Yeah, so I think closure is going to help us, because if I have two things that are regular, say I'm doing intersection, then the result has to be regular. But if I know offhand that the result is not regular, then it can't be the case that both of the original parts were regular. Maybe they're both not regular, but at least one of them is regular. Well, let's see. What can I use closure properties with this to get? Same number of zeros and ones. Have we seen a problem like that before? Oh, I think the 0 to the n, 1 to the n example we did in class, right? Okay, well, let's see. So let's consider L to be that guy. 0 to the n, 1 to the n, and at least 0. That does have the same number of zeros and ones, so L is a subset of L4, but L4 has these, you can have ones and zeros in any order. Well, let's see. How do I relate L4 and L together? Well, let's see. If I'm in here, how do I get down to here? Well, I have to be able to force the strings to have the zeros at the beginning followed by the ones. Well, how do I do that? Do intersection, yeah. So what I'm going to do is L4 intersection something. Well, let's see. L4 says that it's going to have the same number of ones and zeros. That's what the definition of L4 is. How do I get it so that the zeros must come first?
0 star.
0 star, 1 star, right? This enforces the ordering, right? If you're going to be in this intersection, you better start with zeros, then have ones come after it, and have the same number of each, because it's intersection here. But this result is just L. What do we know about L? Not regular. What do we know about 0 star, 1 star? It is regular, and how do you know that? This is a regular expression, so we're good there. I should just say regular. And so what can I conclude about L4? Yeah, I can conclude L4 not regular, because if it were, because we have closure under an intersection for regular languages, L must have been regular, but we already know it isn't. Okay? Yeah.
So on the test, would we be able to use 0 to the n, 1 to the n
Oh, yeah.
as being not regular without
Anything
having
that's
to prove
in the
it?
book, anything that's in the book and we've seen in class and recitations, you're absolutely free to use. Yep. Any other questions? I'll see you next week.
I have a real quick question.